Today we shall be considering the ordinary differential equation. Ordinary differential equation is a derivative expression involving variables. These variables can be state domain variables, which implies the space and time. For example, dy dx is equal to 2x. That is a first order differential equation with space variable x and y. The x variable there is the independent variable, while the y variable is the dependent variable. It is important to know that rate function is accompanied with differential equation, especially the ordinary differential equation. A differential equation can be said to be partial differential equation. So, however, it is pertinent to note that the variables that are integrated in ordinary differential equation are simply the x variable, the y variable, and sometimes the t variables. Now, that is an implication that a state space can be given with respect to time domain, but in a variable notation. However, application of ordinary differential equation cannot be overemphasized, as ordinary differential equation is applicable in resolving biological challenges in population analysis. For example, birth rate, death rate function can be analyzed in a country when doing population analysis. We also apply the differential equation to resolve engineering challenges in electrical engineering, the signal processing. Now, signal processing analogy can be resolved with differential equation with application of a software such as a MATLAB. The usefulness of differential equation cannot be overemphasized, as it also cut across the economics. In economics principles, you apply the differential equation also. It is imperative in almost all spheres of engineering application. Chemical engineering, when you are analyzing a chemical kinetic challenge, you have to apply differential equation. Also, in the field of mechanical engineering, when you are analyzing the simple harmonic motion, the simple pendulum, vibrational concepts, and oscillatory mechanisms, we apply differential equation to resolve most of these challenges in engineering. So the differential equation is important, is key, even though we also apply it in higher spheres in aspects of aeronautics and advanced medicine. So it is important that we take differential equation serious, very, very key. Well, there are also types of differential equation. Basically, we have the linear differential equation, which is likened to normal linear equation. Although the linear differential equation can also be said to be homogeneous and non-homogeneous. When a linear differential equation is equal to 0, it is said to be homogeneous linear differential equation, depending on if it is comprising of one derivative, that will be called first order linear differential equation. If the highest order of derivative is 2, that means it is called second order differential equation, just in that form. Now, it is said to be linear when it is forming a linear equation. Otherwise, it is said to be non-linear differential equation. Take note that in linear differential equation, we also have the non-homogeneous linear differential equation. That is, when the linear equation that is differential in nature is not equal to 0. However, the solving of a differential equation is characterized with different patterns and methodology. Many thanks to great and eminent physicists, engineers, and scientists in the past who has given us the methodology to resolve differential equation challenges with ease. Prominent among them are Sir Isaac Newton, Euler, Clairaut, D'Alembert, Rodrigues, and many other engineers and scientists. They played important role in giving the key to resolving a differential equation challenge. It is quite encouraging, and also it goes with ease in resolving differential equation challenges, both the partial differential, which is of the advanced, and the ordinary differential, which is of the first course. And the dependent concepts related to ordinary differential equations are your basic calculus. What are basic calculus? Differentiation and integration. It is pertinent to review integration very well before resolving first order differential equation. First order differential equation is a bit more wide in scope. Now, what do I mean by this? In first order differential equation, you have the separation of variable technique. In first order differential equation, you also have the linear differential equation, which is characterized by the application of the integrating factor, that is exponential integral p dx. So also in first order differential equation, you also have the Bernoulli's equation. Sir Bernoulli did a great work in resolving first order differential equation problems. And you see, when a first order differential equation is characterized, for example, as dy ds plus py equal to q multiplied by y raised to power n could be any number. That is a key expression or a key connotation of a Bernoulli's equation, and it requires the application of the linear first order differential equation by integrating factor technique to resolve it with ease. So, however, too, we can resolve first order differential equation by exactness methodology, the exact method. The exact method goes with the test of the differential equation. If the differential equation is exact, then you can resolve the problem using the exactness principle. Of course, when partial p partial x is equal to partial q partial y, it is said to be exact depending on the nature of the equation. At that level, we can now use the exactness methodology to resolve the problem. It is not also out of place that many differential equations can actually resolve practical problems, which is often referred to as application of first order differential equation or modeling of problems. Like, for example, electric circuit model, the inductive circuit, the capacitive circuit. So in all of these first order circuit and second order circuit in electrical engineering, you use differential equation solution methodology to resolve such circuit problem. So also it is also used in mechanical engineering, the spring or the damper effect, and also the vibrational challenges, resolving vibrational problem, oscillatory problem. It is easier to resolve some of these challenges in mechanical engineering, like the harmonic motion. The harmonic motion, the likes of y prime prime plus omega square y equal to 0. That I've just mentioned is an homogeneous equation in mechanical engineering, and it has to do with oscillation and with harmonic motion relation. So resolving it, you now use the second order differential equation methodology of solving homogeneous equation to get your answer, where omega is known to be the angular frequency. However, it is pertinent to note that differential equation application is so vast. For example, the perturbation technique. Perturbation technique is an approximating method using numerical solution approach. Of course, it is as a result of your analytical review of the ordinary differential equation that will metamorphose into a perturbation expression for solution that implies numerical value.